I'm going to conclude with some mini videos on more advanced techniques in machine learning. This one talks about trees and forests, and then SVM. Trees and forests go together as naturally as the terminology would have you believe. Tree models are setting up a number of decisions to classify, where each classification creates branches, and with a number of levels, the branches expand out. For instance, if we wanted to model whether a person has health insurance, we might have a list of questions to ask about the person. Are they older than 60-something? Do they have a college degree? Each yes-no question branches off. It creates a model that looks something like a tree with a lot of different branches. The X variables can be continuous or discrete. For instance, in the simple example I just gave, does the person have a college degree? That's a yes-no. But how old are they? That's continuous, but the model can pick a salient age. Now, each of these explanatory variables, the set of X variables, is called a feature. That's the terminology gets used pretty often. The tree model splits based on the X variables, the features, trying to find splits that give the greatest reduction in the sum of squared errors in the Y. It's useful to understand that the goal it's seeking is very similar to the goal of ordinary least squares, or other models like logit or probit. There are many common parts of these solution strategies, because it works. There are other techniques that might minimize the variance of the objective function, maybe absolute value of the errors instead of squared errors. But minimizing the squared errors is the most common. Now, how do we do that in R? The most common libraries are rpart or caret, C-A-R-E-T. I don't have a strong preference for one or the other. I'll just demonstrate with rpart. It creates partitions that look like trees, as you can see from that picture. The model is to explain whether a person has health insurance coverage, and it can choose to use any of age squared, or other typical bits of information. The syntax is straightforward, very much what we're used to. We use rpart in place of lm and add method equals class to tell it that our y variable is 0, 1, dichotomous. If the y variable were continuous, then we'd use ANOVA. That's one tree. But estimating a tree takes a certain artistry, since sometimes they can end up with too many features. That explains within the training data, but doesn't really generalize. The tree can get too bushy, and it would need to be pruned. Yeah, sorry, maybe folks took that metaphor a little too far, but that's genuinely the terminology. Anyway, trees might get too many branches that meticulously classify that particular training data, but not very useful in making predictions out of sample. Statisticians tried to figure out the optimal amount of pruning needed. But alternatively, we could estimate a whole bunch of slightly different trees on slightly different training data sets. We would have a forest of tree models, each tree grown on a random subset of the training data, and that gives us that forest. A forest model would aggregate the predictions of a set of trees. So for instance, if 70% of the trees predict some outcome, then that's the best prediction of the forest working in ensemble. You could create trees from one by one, but that's a pain. It's better to just set the computer to work. It takes a good deal of computing power and time, but it's not hard. But random forest models are very difficult to explain. While trees are simple, those are a set of decision rules, but a forest is kind of a black box. A set of tree models voted on an outcome based on some amount of randomness in the data selection. That's tough if one human has to explain to another human why some decision was made. If the point is just get a prediction, especially if the prediction is low stakes, then forest can be very good. But credit scores, those determine if somebody gets a loan and what interest rate they pay. It's important, perhaps legally obligated, to have a rationale available. Kathy O'Neill has a great book on this, Weapons of Math Destruction. No, I'm not lisping, that's math destruction. It's a problem for lots of public policy if decisions are made that have no available rationale or justification. Perhaps they use data sources that deepen existing inequalities, such as being based on gender, race, ethnicity. it can be a really big problem for making high-stakes decisions. How do we implement a random forest in R? There's a package for it. First, though, we want to use this standardized package. That puts the data into a standardized object, which squishes all the variables into the 0-1 interval, which, recall, we did back with K and N, puts them together consistently and coherently, so we can run a suite of different machine learning packages. That way, each one starts with the exact same data, and it's easier to compare how they're doing. The next step in the code is to call the random forest using that first line, print the output in variable importance. There are two different measures of importance, don't worry too much for now. Get the predicted values from the model, compare them against the actual values of the test set. Remember, that's the new data that's not within the training data that the model hasn't seen yet. That can help test if the model is genuinely useful. Then we get what's called the confusion matrix. Yeah, that's a lot of my life. It's good terminology. I mean, machine learning is very cool. I wonder how much comes from good terminology. I mean, if they called it the matrix of type 1 and type 2 errors, would it be as cool? The consolations of philosophy. Anyway, the confusion matrix is a little 2x2 table that compares the predicted values against the actual values. The off-diagonal terms are errors, and those should be small. But remember, as we've said previously, that false positives or false negatives might have a different cost. There's no guarantee that the cost is symmetric. You should be asking, which mistake is less costly? And that depends on the point of the modeling. You also look at particular subgroups to see if there are some groups of observations that are more confused than other groups. That can help you refine model accuracy. The last technique for now is support vector machines, which has certain similarities with KNN neighbor technique, but a good bit more complicated. I won't go into details for now. The package is E1071 because, as I've mentioned, statisticians have a flair for good terminology. The SVM depends on two hyperparameters which provide different levels of sensitivity. You can think of those like the multiple cameras on your phone. You pick one or the other to get very different viewpoints. Those hyperparameters change the sensitivity to outliers in certain directions of the data. You can use those cost and gamma parameters as given, or you can run the tune.svm first. That tries out different levels of each to assess which perform better on your particular data. It's, kind of a pain since it takes extra lines of code and it takes quite a bit of time. It's computationally expensive. You might have to reduce the size of your training data even more so as not to crash your computer. Sometimes you reduce the training set to make the code work, then raise the size, let your computer run all night long to do the computations. That's getting to be the time of year when you don't mind the extra heat in your home. But the rest of that syntax looks very familiar. You run the model, get the predictions, look over the confusion matrix.